Hello and welcome to ESM. In this tutorial video, I'm going to show you how to make a 2D interpolation using groundwater monitoring data. Let's start with the basics. What exactly is 2D interpolation? Well, it's the process of estimating values between known data points on a two-dimensional grid. Essentially, we're filling in the gaps or missing values in a grid, based on the values of neighboring points. It's like connecting the dots to create a complete picture. Imagine you have a set of data points scattered across a grid, just like you see on your screen. However, there are areas within the grid where you don't have data points. That's where interpolation comes in handy. It helps us estimate values for those missing points by considering the values of nearby known points. In essence, 2D interpolation allows us to make educated guesses or approximations about the values in nodes where we lack direct data. We base these guesses on the patterns and relationships observed in the known data points. Now, before we begin, I want to mention that we'll be building upon a previous project. If you're feeling a bit confused, I recommend checking out our previous videos where we explain how to build up to this level. Today, we'll be working with groundwater monitoring data, but keep in mind that 2D interpolation models can be made using other types of data as well, such as soil data or soil-air data. Also, for simplicity, we'll focus on only two compounds, but in reality, there can be many more. Let's get started with the practical steps. First, we need to navigate to the Data Manager window and double-click on the GWM log file. A pop-up window will appear, and we'll go to the Outputs tab. We'll navigate the mouse over the empty window and right-click to select the Add function. On the top of this window, we need to choose the output type. For this example, we'll choose 2D interpolation. Right below, we need to choose a location for our file. In our project folder, we have a folder named Outputs. We'll place the file there. Now we need to decide the compound we want to interpolate. In this case, I'll choose TC or trichloroethylene. So, let's set the file name and press Save. Next, we need to choose a value to interpolate, and as we decided previously, it will be TC. Now, let's take a look at the Algorithm tab. You'll notice that we can choose the type of interpolation and settings regarding the algorithm. In this video, we won't dive into the different algorithms, as it's beyond the scope of this video. But one common type of interpolation is IDW, which stands for Inverse Distance Weighted. For now, we'll leave this tab as it is and move on to the Geometry tab. Here in the Geometry tab, we need to choose the window of our interpolation. You'll see some coordinates already populated, so we leave them as they are. Below that, we choose the spacing of our interpolation. This determines the size of our grid cells. Just like we saw on the screen before, we can have smaller cells or larger ones. A smaller number means more calculations for the algorithm, but better detail in the model. Conversely, a larger number means bigger grid cells, resulting in a rougher model but faster calculations. The choice depends on the area you're working in and how much detail you want in your interpolation. For this example, we'll leave it at 1. Now we need to jump back to the coordinates. To make the interpolation fit in the coordinate window, we will make them divisible by our spacing. This means that we will round up the coordinates to match our spacing. In this case, it is quite easy as we will just delete the numbers after the point. But if we would choose to, we would add or subtract the values to make them divisible by 2. By right-clicking on the window, we can save our adjusted coordinates as default by choosing Set Project Grid Geometry Default. So, when we make more interpolations, we don't need to set the coordinates again. Now let's move on to the Search tab. Here, you'll see X and Y radius values, along with AZ angle. These search values are crucial in the interpolation process. They are the search values used as references in order to estimate values at unknown locations within the grid. The algorithm searches for the nearest or most relevant data points to the location and estimates a value for the grid node. To estimate accurate values, let's quickly jump into our project. Here in our project, we'll use the measuring tool from the top to estimate the distances from point to point. By left-clicking on one of the points in the middle, we can move the mouse around and see the distance between the points. From several points, we see that the values vary, but it's about 15 meters. So, let's jump back to our interpolation. In the X and Y values in the Search tab, let's set it to 15. Since we have no information regarding the angle, we'll keep the Z value as 0. Now, let's move on to the Value tab. Here, we refer to the approach used to estimate values outside of the search radius. Sometimes, the target location falls outside the range of known points, meaning there are no found values within the defined search radius. In such cases, we need to make an assumption or strategy for estimating values outside the search value range. In this example, if we have a grid node right at the corner of the grid, we'll assume its value is 0. So, let's tick the box to activate that function. We'll leave the other settings as they are, as we want to see all the data interpolated. Now, on the right, you'll notice a tick box in the duplet section. However, that's for another algorithm, so we'll skip that for now. Let's move on to the Smooth tab. The Smooth function is a post-processing step that aims to reduce abrupt changes or noise in the interpolated grid. Sometimes, the interpolation process can result in a grid with sharp transitions or irregularities, especially when the distribution of known values is uneven or when there are outliers in the data. In simple terms, this function helps us create a nicer-looking picture by sacrificing some precision. Let's tick the active box. You can always compare the visualization without the smoothing function to find the best fit for the data. Last but not least, we have the Blanking tab. This function is used as a post-processing tool for modeling. It allows us to cut out values that exceed out of the boundaries of interest. However, this is also beyond the scope of this video, so we'll leave it unchecked. Now that we're done entering all the settings for our interpolation, it's time to click on Execute in the bottom left corner. ESM will start calculating our model. Once it's done, click OK and then OK again. In the Data Manager window, you'll see an arrow coming from the GWM file onto the GRD interpolation file. Left-click and drag the file onto our map. You've just applied the interpolation. I want to emphasize that this is an iterative process. It means that we can modify the interpolation and fine-tune the model based on different parameters and changing conditions. Initial assumptions or settings may not be perfect, so continuous refinement is necessary to improve the interpolation. To illustrate what I mean, I will quickly import a legend and change some of the settings. We can head back to the interpolation output again and on the spot make some adjustments. For example, let's go to geometry and say we do not need the grid nodes to be so small, so we increase the horizontal spacing value to 2 meters. By simply pressing execute, we wait for the software to finish interpolating, and we have an immediate update on what happened when we done that. We can go to Search tab and decrease the X and Y values to 10 and see how this change will affect the model. We can do the same for the Values tab where we deselect the active checkbox. We can also uncheck the Smooth tab and by clicking Execute again see the result. Well, that's all for this tutorial video. In our next video, we'll explore more aspects regarding the visualization of this model. Thank you so much for watching, and as always, if you have any questions, feel free to contact us.